What is going on? As always, I hope no matter where you are, you're having a fantastic time. I hope things are going exceptionally well for you. Now, my name is Dr. Jason Dinsmore, aka the OChem Whisperer, and I want to help you succeed in your organic chemistry class. Now, what are we going to specifically be covering? We're going to go over how to understand bromination of alkenes. Remember, we've been doing right now, we're working on alkenes. A lot of you are probably working on alkenes. Some of you might be working on alkyl halides. I know from semester to semester it kind of switches, and professor to professor it kind of switches, but right now we're going to be going over alkenes. So for those of you that might be jumping on now and are working on substitution, SN1, alkyl halides, all that, you can watch the previous lecture, but I also want you to stick around if you're not working on alkenes yet because you'll kind of get a head start. All right, so we're going to be talking about bromination of alkenes, and essentially this is kind of the basic thing that we're going to be going over for every single reaction we go over. We're going to look at the overall reaction. We're going to talk about stereochemistry. If there is any, in some cases there won't be any. And the last thing is we're going to go over the mechanism, all right? So let's go ahead and take a look. So the basic reaction of the alkene with the bromine will give us this product right here. And remember in one of our previous lectures, we talked about how a double bond can react in two ways. We can take the double bond and add a group to each side, one on each side like we did here, or we can take one atom and add it to both sides, kind of like epoxidations that we've talked about. Now, we're going to find out here when we do the mechanism, we're actually going to form a three-membered ring with just the bromine, okay? But initially, when we get the final product, when we think about this, we want to add a bromine to both sides. So this is kind of an easy reaction to break down. We have our function group, which is an alkene. We only have one reagent, and it has two things to it, and we're just going to put those two things on each side, okay? So this is a very easy reaction scheme to break down. Now, the thing is, you see that I have straight lines right there? Actually, with the bromination, we get trans stereochemistry. So when you draw these products out on an exam or a quiz or your homework, when you work in problems, you want to make sure that one of your bromines is a wedge and one is a dash. Now in this case, I did wedge dash. You could have done it the other way, dash wedge. You just want to make sure that your overall stereochemistry is trans when you do your bromination. And we're obviously going to go into the mechanism and explain why that's happening, all right? So just remember that it's trans stereochemistry. All right, so let's go ahead and take a look at the mechanism and see why this is trans, all right? So we want to remember with every single mechanism, we start our arrow at our nucleophile and we move the arrow towards our electrophile. So it's always a minus or partial minus to a positive or partial positive. So in this case, our bromine is going to be our nucleophile, and in step one set of the lone pairs is going to attack the double bond, okay, the alkene. Now remember in one of the previous lectures we talked about alkenes are both nucleophiles and electrophiles. And if you happen to miss that lecture, you can go ahead and rewatch it. Stick around for this one, of course, you can watch it later, but I think it was alkene's introduction. We talk about how you can look at an alkene and figure out which side's the electrophile and which side's the nucleophile, but alkenes or double bonds are both. So in this case, our nucleophile, which is our bromine, is going to attack our double bond. That's step one. Step two, then our double bond is actually going to come back and attack the exact same bromine that just attacked. So if we follow those arrows along, remember it's always from nucleophile to electrophile, so we can see that what we're actually going to form, if we took those arrows and actually formed lines, we're going to see that we're going to form a three-membered ring, okay? Now in order to finish this mechanism, the bromine attacks, the double bond then attacks the same bromine, then what we're going to see is that the bromine-bromine bond is going to break, okay? And we're going to generate a Br-, and it's going to look something like this, okay? So we can see that now we formed a three-membered ring with a bromine. It's called a bromonium ion, okay? And we also have a Br-, okay? So we can see we're not there with the two bromines on both sides yet, but we're getting close. Now we can see here in this case we've got a three-membered ring with a bromine. So we've talked about the fact that we can form three-membered rings with double bonds. We can form this bromonium ion, and you'll also see in a later lecture that we'll talk about is epoxides if you haven't seen that already, okay? Now this right here is going to be a transient intermediate. This is not going to stick around. We're going to react with this, all right? Now the other thing that we have to consider here is the stereochemistry. So once we do all the arrows, the bromine attacks, and then the double bond attacks the bromine, and then the bromine-bromine bond breaks, we want to remember that we have to put our stereochemistry in at this stage to show our professor that we know this is ultimately going to give us a trans. So since this is a three-membered ring, it's impossible to have trans stereochemistry with a three-membered ring. It's too strained, okay? So when you draw this, your bromonium ion is always going to be cis. So they're either going to be wedge-wedge or dash-dash. It doesn't matter which one you choose. You just need to pick one, okay? So remember, wedge, dash. We're going to start out with this cis stereochemistry once we form our three-membered ring, all right? So go ahead and take some time just to make sure this makes sense in terms of our arrows and forming the bonds and breaking bonds, okay? All right, so hopefully now this is kind of making a bit of sense. All right, so now let's go ahead and finish out the mechanism. So we bring our bromine on there, it attacks, the double bond attacks the bromine, we break the bond and we get our bromonium ion. In this case, I'm going to do the cis with the wedge. Now we've got our Br-. that's going to come back in. So remember, it's always nucleophile to electrophile. So our Br is minus, our nucleophiles are negative. It's easy to remember, N and N. And then we're going to attack our electrophile. And when we do that, it's going to attack the carbon, not the bromine. And when it's kind of like an alkyl halide, right, for those of you that have studied that. So we're going to attack that carbon, and then we're going to break the wedge, the red wedge bromine carbon bond, which is going to open it up here. Now there's a key thing that I want you to notice here. See how our bromine attacked that wedge, that red wedge Br? And now look at the stereochemistry on that Br over there. It's dash. What is that? So for those of you that have studied essentially alkyl halides, that's an SN2 reaction, right? It may not look like it at first, but that's almost like a quote-unquote alkyl halide. It's a strange one, I know, but that's an alkyl halide. And all we're doing is we're taking a nucleophile coming in, attacking alkyl halide. SN2 reactions always give us an inversion. So that's why we're getting the trans stereochemistry. We can see the black wedge on the Br, we didn't touch that, so it stays exactly the same. We don't change that one. We only change the one that we attack. So that's why we're getting the trans stereochemistry on the bromide. And we can see here that that's just going to be an inversion at that stereochemical center, okay? Does that make sense? Am I making sense in terms of that? Okay, cool, awesome. All right, now, let's go ahead and take this right here, okay? So let's take this molecule, let's slightly modify it with the methyl, and let's add a Br2. So what I want you to do at this point in time is I want you to go ahead, based off of what we've done and what you've learned in your class, I want you to go ahead and predict what the product would be on this one. So go ahead on your electronic pad, you can write it, or on a piece of paper, or just in your mind, but I want to make sure that you're working on this. So I want you to work this problem before I get there to make sure that you can see, you can work out all the kinks here so you can crush your organic chemistry class in your exams, okay? All right, so I'm hoping that you took some time. Now for this one, there are two different ways you could have drawn this. You could have drawn this way. The first one that I see in the products is wedge dash bromine, or you could have done the second one, which is on the right, which is dash wedge. All that's important here, that's key, is that you have your trans stereochemistry of your bromination, okay? So the way that you want to work this problem is the way that I'd recommend this is you take your 6-membered ring with your double bond and you draw your trans stereochemistry of your bromine. So draw a wedge dash or dash wedge. Then if you have any substituents hanging off of any of those carbons where you've added your bromines, in this case we have a methyl, then draw the opposite, meaning the fact if you have a wedge bromine, then your methyl is automatically dash. If you have a dash bromine, if that's the one that you drew, then your methyl is going to be a wedge, because you always have to have a wedge and a dash. So once you draw your bromines, your other group is going to be the other, whether it's a dash or a wedge. So you could have drawn either one of these, all right? Now, let's go ahead and look at the mechanism, okay? So we've seen this before, that our bromine is going to attack the double bond, then our double bond is going to attack the same bromine, then we're going to break the bromine-bromine bond, okay? Now you might be saying, well, Jay, okay, you're attacking that side. Does it matter which side the bromine attacks? Yes, and I'm going to explain in a minute, okay? But first what I want to show is I want to make sure that you drew, essentially, if you're doing the mechanism, if you're working through it, that we draw our mechanism. Remember, our bromonium ion is cis. So what we have to make sure to do is we draw our bromonium ion either wedge or dash. And in this case, since we have a methyl group or a substituent, we have to make sure we draw that stereochemistry as well. So if we have the bromine wedge, our methyl is dash. If we have the bromine dash, our methyl is wedge, okay? And we've got our bromonium ion like that, okay? So just once again, make sure that this all makes sense. Is it making sense? Cool, awesome. All right, so now the question is, if we have this bromonium ion, which we do, obviously, which side's it gonna attack, right? So if we look at this, and we kind of thought about this, we might look at this and say, okay, if we look at the left-hand side with the red wedge, that looks like a secondary carbon, okay? And if we look at the left-hand side, that looks like a tertiary carbon, right? And so we see that there's a difference in substitution, and we've talked about that with SN2 reactions as well, or substitution reactions. Let's put generally substitution reactions. We've seen that substitution, the patterns make a difference. So if you look at this, what I want you to start thinking about in terms of the bromonium ion is that there's 3 different atoms this carbocation can be on, okay? We can either have it on the bromine, which is the one we've seen so far that I've drawn, or we can imagine that carbocation could be on the middle structure on the secondary carbon, or we could have it all the way on the right on the tertiary carbocation. What I really want you to think about, this is positive charge. Imagine it's like in the middle of that 3-membered ring. The reason I didn't put it in there is because it'd be hard to see, because it'd be really small, right? But we want to imagine it's kind of choosing between these. It's kind of like on all these atoms. But we want to figure out if we had a carbocation, which place would it rather be? Now, bromine is not the one we want to put it on, right? Because bromine is electronegative, and electronegative atoms want negative charges, not positive. So we're going to rule that out. So between that, bromine is more electronegative than carbon. So carbons are our only other choices. Now what we're looking for, since they're both carbon, is we want to look at the substitution. And if you remember, carbocation stability works with tertiary is better than secondary, which is better than primary. So in this case, I'm hoping that you all chose to figure out which one of these would be best. would be this one right here, because that's going to give us a tertiary carbocation. Now this is not a full-on carbocation. That bromine is not completely fallen off, and that's a full carbocation that's flat, sp2 hybridized, but it's going to be semi-flat, and that carbocation is going to be kind of like that, okay? So it's kind of like a partial charge, but if we had essentially all this, it's going to probably reside on that carbon the most, okay? So that's going to be the most partial positive part. And why that's important is because we always have a nucleophile which is negative or partially negative, and we have an electrophile which is positive or partial positive, and our nucleophile always attacks our electrophile. So in this case, what we've discovered is where our electrophile is and what's going to get attacked, okay? So now we know, this makes sense, right? Now our bromine, which is negatively charged, is going to attack that partially positive carbon, which is tertiary, because it can house that or stabilize that carbocation better. Then we wind up getting the stereochemistry, okay? Now, once again, make sure, look at this, we've got our black wedge to our bromine. Now in our final product on the right, it's a dash. So remember to invert your stereochemistry, okay? When you're doing your mechanisms, make sure that your bromination is always trans. And then once again, our methyl is going to be wedge because those things invert, okay? And once again, it's just like an SN2 reaction. Or I guess we should say it's just like a substitution reaction, since we kind of got a pseudo-carbocation. Let's think about it as substitution, all right? That might be a better way, all right? Cool, does that make sense? Awesome. All right, now, let's take this same starting material and the same bromine, but let's add something. What if I dropped in below the arrow, boom, some water? What do you think is going to happen in this? All right, I want you to go ahead and predict the product. Is this just like a solvent that's going to make it go faster? Is the solvent going to react? Is it a solvent? Is it a reagent? What is it? All right, what do you think the product is going to be? Is it going to be the same what we saw? Is it going to be different? Go ahead and take some time to figure out that, all right? So some of you may have seen this, some of you may have not, but even if you haven't seen it, just try to think in your mind what might be happening here, okay? Thinking about the mechanism. All right, so I'm hoping that you took some time to do that. Let's go ahead and look. So boom, we get this, all right? Now if we look at this, let's check this out. We don't have two bromines, now we have an OH and a bromine. But we want to notice in this case right here that they're trans. So our OH and bromine are trans, just like our bromine and bromine were trans. The difference here is that we can see we had an OH come in rather than another bromine, all right? So do any of you have any ideas of how this might have happened, thinking about the mechanism? All right, so let's go ahead and take a look at that. So first, I want to make sure I'm hoping that you got one of these two things. Remember, it doesn't matter if we have wedge dash or dash wedge, we just have to have trans stereochemistry. So the water is going to participate, all right? So let's go ahead and take a look here. Now we know how to form the bromonium ion. We've seen that twice, and so we've got that. And remember, it has to be cis, so we either need wedge, wedge, or dash, dash. Now what's happening is instead of the Br minus attacking, the water is coming in as our nucleophile. So now we've got our arrow going from our nucleophile, which is our water, to our electrophile, which is specifically that carbon, and that's going to attack, and then that's going to open up the bromonium ion, okay? So in this case, we've talked about this. This is kind of like a quote-unquote substitution reaction. We get our inversion of stereochemistry, but now we can see we're not at the product. Like, remember we had our bromine come in, we added the bromine just like that, we're done, we have our product. With water, we've got this extra hydrogen that we have to get rid of, okay? And so when you essentially have a hydrogen that you don't want, it's called a proton transfer. It's kind of a fancy term for moving a hydrogen around. So we're almost to the product, we're not there yet. So we have to get rid of that hydrogen. So what we're going to use is there's going to be tons of this water floating around. So we're going to do this proton transfer where essentially we have our water molecule is going to pull off just the hydrogen, leaving the bond, and then those electrons are going to fall back down on that oxygen as a lone pair. And when we track through there, now we've got our final product, and we can see that we've generated H2O+, which is just acid and water, okay? So once again, this is just a proton transfer when we take one water molecule and transfer that hydrogen to another. And the reason we want to do that is obviously our product. When somebody did this reaction a long time ago, and people that have been doing this, they discovered the fact that they get an OH, not the H3O+. So we've learned this mechanism through doing the reaction. But in this case, we have an extra step because we have that extra hydrogen. So we wind up once again getting our trans stereochemistry right here, and then we get this acid left over. All right, does that make sense? So in this one, we just have an extra step, but pretty much it's the same mechanism. If you understand the mechanism, it's basically the same over and over again. So the key points here is to remember the stereochemistry, and remember to see if their substitution around your double bond is different, because when you actually do your mechanism, you're gonna want to take that into account, all right? So cool, and as always, that's all I have today, but as always, thank you all so much for coming on here. I literally can't tell you how excited I get that all of you come on here, and I get to kind of interact with you and share what I've learned over the years. And with that, until next time, I hope you all have a good one.